What is up, guys? I wanted to talk about this problem I had in electromagnetics that I thought was really interesting. We have this both spatially and time-varying magnetic field going through a stationary loop. The loop is a square centered at the origin with side lengths 20 centimeters, and it's 10 loops. And we want to find the current that's driving or that's going into this 1 kilo ohm resistor. First steps to find the emotional EMF. So VEMF TR is going to be equal to negative N times the change in flux, the magnetic flux going through this area with respect to time. So this is going to be equal to negative 10, since we have negative 10 loops, times the time derivative of the magnetic flux, which is a surface integral of B dotted with ds. And let's talk about what our ds vector is first. So our ds, we have a differential area that the magnetic field is going through. It's going to be a square, and its direction, the direction is the normal direction, is z hat, and it has a width in this direction going to be a differential y, dy, and width in this direction, dx. So dy dx z hat is going to be ds, and we're given b here. We could plug in 100 there. So we have, this is equal to negative 10 times d over dt, surface integral. And so to set up the bounds here, we want to find where is y, what parts of y are we integrating over and what parts of x are we integrating from. So since it's centered, we're going to go in the x direction at least. We're going to go from negative 0.1 up to 0.1. So negative 0.1 to 0.1. Same thing in the y direction. We're going negative 0.1 here to 0.1 there. So negative 0.1 to 0.1. We can plug in b naught, so 100, and then x squared times cosine of 10 cubed t, and then we're going to dot that with, and this is in the z hat direction, dot that with dy dx in the z hat direction. That dot product, since they're both in the same direction, eventually becomes a magnitude of 1. So we get negative 10 number of loops. Let's go ahead and pull that 100 out right away, times 100. We can pull out the time varying stuff as well. So the derivative is going to go on that, d over dt of cosine of 10 cubed t, like that. And then inside, we're going to have negative 0.1 to 0.1, negative 0.1 to 0.1 of x squared dy dx. Here, and we can even separate that out more. This is just going to be equal to, we could take this derivative now, we get negative 10 times 100 times negative 10 cubed sine of 10 cubed t multiplied by integral negative 0.1 to 0.1 of just dy, and then negative 0.1 to 0.1 of x squared dx. This one here becomes 0.2. This one is x cubed over 3 evaluated from negative 0.1 to 0.1, which is equal to 0.1 cubed over 3 minus negative 0.1 cubed over 3 equals 0.1 cubed plus 0.1 cubed over 3. So now we have everything. If we multiply it all together, this negative sign cancels this negative sign. We get 133.3 times sine of 10 cubed t volts, and that's equal to V EMF transformer. So it's positive. We know that the positive terminal ends up here. Since we have our ds direction like this, our 4 fingers are going to go through this terminal first. And we've also drawn our current direction here from positive to negative. So now let's find the current. To find current, use Ohm's law. V is equal to I times R. So I equals V over R. Since our resistor is 1,000 ohms, we get 133 divided by 1,000 sine of 10 cubed T amps, which is the same thing as 133 sine of 10 cubed T milliamps. So that's the current. And so we can imagine the current's going to be changing over time. So we have alternating current as it is. So it's going to go, it's going to go this way sometimes, it's going to go this way sometimes. That's what's the alternating part about it. So that's pretty much how we tackle a problem like this. Hope that was helpful in kind of explain the process. Main steps here are to identify our fundamental equation, plug values in, evaluate surface integrals. The d over dt is coming from here. We're doing the time derivative of the flux. And yeah, we do some integration techniques here that you learn in Calc 3. If we have things just multiplied by each other, we can separate them out because we can basically put, if this inner integral is with respect to dy, we can take this dx and this dx over here. And that's how we did the dy first, and then the x squared dx part second, multiply them together. And yeah, that's pretty much how you would tackle a problem like this. And hopefully that was helpful. Thanks for watching.